So for our second example, we want to use mathematical induction to prove that the statement Sn is r times cosine theta plus I sine theta, quantity raised to the power n, is equal to r raised to the power n times cosine n theta plus I sine n theta, is true for positive integers n. Where to do this, we're going to follow the same kind of process as before. We're calling into mind that we are going to perform some kind of proof here, and we're going to start with our base case. Well, at S1, we have the somewhat obviously true statement that I should put U inside of there, and that should be a parenthesis. And again, I'm going to use that shorthand notation CIS theta just to save myself some space and hand cramping. But we're going to say that that raised to the power 1 is equal to, well, r to the 1 times CIS of 1 times theta, or r times CIS theta. Okay, hopefully we can tell that that's definitely true, that something raised to the first power is just, well, the something. So we have that the base case is true. So next, we assume that for some integer k, so the shorthand notation for that is k in, and then we draw a bold z to notate the integers. Don't worry too much about that notation. It's just a shorthand there, where actually it should be even more specific that we're talking about the positive integers. We have that sk is the statement r CIS theta raised to the power k is equal to r to the k times CIS of k theta. We assume that this is true. To show that the k plus 1 version, where that is the slightly uglier r CIS theta to the k plus 1 is equal to r to the k plus 1 of CIS k plus 1 theta. And this one takes a little bit more logic, takes a little bit more understanding here. But what we're going to do is take this left side and use the same sort of idea as before to try and pull things together into as nice a pattern as we can get. Where, starting over here, well, we can factor out 1k, but a whole bunch of them technically, and we'll have r CIS theta raised to the power k multiplied by, and to move this over a little bit, r CIS theta, where we can be sure that this term here happens to fit nicely in that way, based on what we saw up there. That's technically that thing raised to the power 1, but it does what it's supposed to. And on this side, well, thanks to the base case, we can say that this is equal to that. That we have r raised to the power k times CIS k theta times r CIS theta. That there. And we're still hoping that this holds. It shouldn't technically be equals just yet, but we're going to see that it does work. Where we can pull in that r. I'm going to move this over here for a reason. And then I'm going to expand these things out where it's CIS k theta times CIS theta. It's not going to be very pretty, but a lot of things are going to be able to come together. That in here, we're going to have, well, cosine of k theta times cosine of theta plus I squared times, sine of k theta, sine of theta, plus, oh boy, I times cosine k theta, sine theta. I'm just going to put a box around that equal sign to notate that it's coming back around. It's not going to be very nice, but we have that, and then we have another I term where here we're going to have I along with sine of k theta, it's not sinc theta to be clear, times cosine of theta, and bad. This quite bad, not least for the fact that it doesn't fit anywhere near into the notation I want. But, well, we're going to see that a lot of these things come together nicer than they look, but unfortunately I have to erase some of that at the top and move back up there, so reconvene in a second. Now, picking that back up, looking down here, well, for one, let's just bring that r to the k plus 1, because that's going to have to come to the party. We have cosine k theta times cosine theta. I squared is -1, so we're going to have this guy minus sine k sine, where cosine of some angle times cosine of a different angle minus sine of that same first times sine of that second actually simplifies down nicely using the sum of angles formula for cosine, that what we're going to get there is cosine of k plus 1 theta and then over here we've got the i's we can factor out, and we have cosine sine plus sine cosine with those split angles. So this actually just ends up being I sine of k plus 1 theta. And actually, r to the k plus 1 cosine k plus 1 theta plus I sine k plus 1 theta is r to the k plus 1 CIX k plus 1 theta. So this is true. That is, our inductive step holds, and by mathematical induction, the statement, that is de Moivre's theorem for complex powers, is true. Up to, well, my ability to have space on a whiteboard. But that's the idea here, and that's the idea for any inductive proof. Just like the first one, even though this is admittedly a nastier proof than what you'll probably see at any other point in this class, but like I said, I promised I'd do it. It still does fit a lot of nice things in here. It shows us a whole bunch of important patterns with how these things come together, and it's a good example of induction. It's a pretty straightforward one. It's just a little bit nastier for our formulas than we normally see. But anyway, that's what you do. Show the base case, then use k to get k plus 1, and you've got a good argument. And the last thing we're going to see for this chapter, the last thing we're going to see for, wow, this semester, is a look at one more result that is back a little bit more applied, where we're bringing in some things with factorials that we saw earlier, as well as a thing that you may have seen from stats, but with a different name, where in this context, we're going to call it the binomial coefficient, and we're going to use it to develop a idea called the binomial theorem. But that's next. I'll see you in there.